Assalamu alaikum dear students. Welcome back to the multivariable calculus series. In today's lecture, we'll discuss one of the most important concepts in multivariable calculus, physics, engineering, computer graphics, and machine learning, and that is vectors. So vectors allow us to describe not only how much but also in which direction. So by the end of this lesson, you will be able to define vectors in 2 and 3 dimensions, compute vector magnitude, find unit vectors, perform vector addition and subtraction, multiply vectors by scalars, and use of vectors to represent displacement in space. Okay, let's begin. So in physics, mathematics, and engineering, we encounter with two types of quantities which are very important, scalars and vectors. So scalar quantity is one that possesses only magnitude, and it can be specified by number along with the unit like length, mass, time, density, temperature, distance, etc. What if you tell a friend, I walked 5 kilometers? Have you completely described your movement? The answer is no. You also need a direction. For example, 5 kilometers north, or 5 kilometers south, or 5 kilometers east. All have the same distance but different directions. So a quantity having both magnitude and direction is called a vector. So in this screen in front of you, you can see distance is a scalar quantity and displacement, which is a measure of where you are from a fixed point, is a vector quantity. So distance is scalar and displacement is a vector quantity. Other examples of vectors are velocity, acceleration, weight, force, momentum, electric and magnetic fields. So a vector is represented graphically by an arrow. And geometrically, a vector is represented by a direction, line segment with initial point A and terminal point B. So this arrow shows the direction of the vector is from A to B. And vectors are also denoted by some bold letters or sometimes underlined letters like V underlined or V bold. Magnitude, length or norm of a vector is absolute value, and it is written as line segment AB, length of line segment AB, or simply AB, or sometimes absolute value of AB or norm of AB. So all these are the notation of the magnitude or length of the vector. Now there are some special forms of vector, special types of vector, like unit vector is the vector whose magnitude is 1. Null vector is the vector whose magnitude is 0. That is, initial and terminal point of the vector coincides, then the vector becomes a null vector. And a vector is said to be negative of the other vector if both have same magnitude but opposite direction. Like if we have this vector AB, then its negative would be BA. Negative of AB is BA and their magnitude is same. So if we multiply a vector by a scalar k, then the resulting vector has the magnitude k times that of the vector v. So if we have a vector v and we multiply this with a scalar k, if k is positive, then it has same direction as v. But if k is negative, then v and kv have opposite directions. Two vectors are said to be equal if they have same magnitude and same direction. Two vectors are said to be parallel if and only if they are non-zero scalar multiple of each other. Like if we have vector AB, then 2AB is parallel, negative 2AB is also parallel to AB, 3 by 2 AB is also parallel. So any scalar multiple of AB is parallel to AB. Addition of two vectors can be seen with the help of triangle law of addition. If we have a vector u which is represented by the arrow AB, and we have a vector v which is represented by the arrow BC, that is initial point of the vector v is the terminal point of vector u, then the addition resultant vector can be represented by the vector AC, and this is called triangle law of addition. So AB plus BC vector is equal to AC vector. And this can also be represented in terms of parallelogram if we have two vectors AB and AC. And in this case, we have adjacent vectors, like their initial point is same. Then in order to find the addition, draw a vector equal to vector AB, which is vector CD. Then AB plus AC is actually AC plus CD, and it can be represented by the diagonal AD. So AB plus AC is equal to AD. And the other diagonal BC can be represented by their difference. We'll learn in next slide. So subtraction of vectors. Again, if we have vector AB and AC, then difference of AB and AC is actually the sum of AB and negative of AC. So if we have vector AB and AC, then draw the vector which is negative of AC. And now we'll try to add these two and find the resultant, and that would be the difference of these two vectors AB and AC. And using equal vectors, draw a vector which is equal to AB, and then add these two. So this is the vector in red color. This one is the vector AB minus AC. So you can see that this diagonal was the sum of AB and AC, and this is difference of AB and AC. This can be shown in this figure. The vector whose initial point is the origin is called position vector of that point, like this. This is the position vector of any point P. And if we have two vectors A and B, which are the position vectors of 2 points A and B, then the vector joining A and B, that is vector AB, is the difference of these two vectors, B minus A. AB. AB means the position vector of terminal point minus position vector of initial point. So this is how we can interpret this. So any vector which is not a position vector, or which whose initial point is not origin, can be found using this. Okay, let's discuss vectors in plane. That is, vectors represented with the points in the plane. So we know that plane is the collection of all the ordered pairs like xy, where x and y both are real numbers. And if we join any point in the plane with the origin, OP is the position vector of that point. And it can be written as u is equal to xy. And you can see that here we used the square bracket notation, and this is actually the vector notation. So when we have to write the point, we'll use parentheses, and if we need to write the vector, we'll use this square bracket. and x and y are called components of this vector. Now we'll define all the properties of vectors in terms of components. If we have two vectors with components x, y, x prime, y prime, as shown in the figure, u and v, then their sum is the sum of corresponding components. So u plus v is actually x plus x prime. Its x component is x plus x prime. Y component is y plus y prime. So by adding corresponding components, we get the sum of these two vectors. Similarly, if we have a vector u x whose components are x, y, and alpha u will be the vector whose components are alpha x and alpha y. So multiply each component by alpha. Negative of vector is negative of each component. Difference of two vectors is the difference of corresponding components, like this. U minus v is x minus x prime, y minus y prime. So its components are the difference of corresponding components. Zero vector is the sum of the vector and its negative vector. And zero vector has both the component equal to 0. Equal vectors, if their corresponding components are equal, vectors are equal. And position vector we have already discussed. Magnitude of a vector is defined to be the length of the vector, right? So if we have this vector u, OP, whose components are x and y, then magnitude of this vector is length OP. So in order to find length OP, we draw this right angle triangle. Now OP is the hypotenuse of this triangle, and this is the angle which is right angle. So with the help of Pythagoras theorem, this OP length is actually x square plus y square square root, right? And this is the magnitude of this vector. So if we have a vector in component form, so just square both the components, add them, and then take square root. You will get the magnitude of the vector. So there are few properties of magnitude. Magnitude is always greater or equal to 0. So if it is equal to 0, then actually vector is a null vector. And magnitude of a scalar multiple is the absolute value of scalar times magnitude of the vector. Another notation for representing vectors in plane. So for this, let's consider unit vector one zero along x-axis and denote it by I. And similarly, we have a j vector whose components are 0, 1, which is unit vector along y-axis. Then any vector in this plane can be written in terms of I and j. Like if we have a vector u whose components are x, y, it can be written as x0 plus 0y. When we add these two, you will get xy. And it can also be written as x times 1, 0. X is a scalar, x is a real number, so it can be taken out, plus y times 0, 1. So this is I, this is j. So we have xi plus yj. This is the vector xi plus yj. So if you have a vector in terms of components, then you can write it in ij form. Similarly, if you have this vector, you can write it in this component form. So any vector discussed in previous slides can be written in these vectors I and j. If we have a vector u which makes an angle theta with positive x-axis, so we want to find its components in terms of theta, right? So this is length OP, or you can write it as, if this vector is V, so this OP length is V magnitude, and this is X component, and this is Y component. So let me write X over V magnitude is equal to, and this is right angle triangle, this is cosine theta, right? So X is equal to V magnitude times cosine theta. Similarly, you can find Y component, which is equal to V magnitude times sine theta. So this vector can be written as V magnitude cos theta, V magnitude sine theta. So if angle that vector makes with positive x-axis is given, you can find its components in terms of that angle. So if we have a vector V with any random arbitrary direction, which is not a unit vector, if you are required to find unit vector in this direction, then just divide the vector by its magnitude. You will get unit vector in that direction. And unit vector is the vector whose magnitude is 1. For example, if we have 4i plus 5j, so this is not a unit vector because its magnitude is not equal to 1. So let's find out its magnitude. Is equal to 9 plus 25 and square root, right? This is 34 square root. So if we divide this vector by its magnitude, 4 over square root 34 I plus 5 over square root 34 j, then this is a unit vector in this direction. So let's verify that this is a unit vector by taking magnitude. Let it be V hat. So V hat magnitude is equal to, oh, that was 16, my bad, sorry. That was 16. '41. So let me correct it. 41. So 16 over 41 plus square of the y component, 25 over 41 whole square root. And this is equal to 41 over 41, right? And this is equal to 1. So this is a unit vector in the direction of given vector v. Okay, let's extend the idea of vector in plane to the vector of vector in space, that is from 2D to 3D. So again, we have a point in 3D. Then the vector, position vector of this point is OP. And it has 3 components. In plane, vector had 2 components, and in this case, we have 3 components of the vector x, y, and z. And addition can also be defined in similar fashion by adding corresponding components. We get the sum of the vectors. And if we have a unit vector along x-axis given by 1, 0, 0, along y-axis given by 0, 0, 0, 1, 0, and along z-axis given by 0, 0, 1, then any vector in space with components x, y, z can be written as a linear combination of these vectors by doing few steps like we did in case of vectors in plane. It can be written as 1, 0, 0 plus y 0, 1, 0 plus z 0, 0, 1. So it can be written as xi plus yj plus zk. So every vector in space can be written in terms of I, j, k. And similarly, you can define negative of a vector by taking negative of every component. difference of two vectors can be defined by the difference by taking the difference of corresponding components. Zero vector is the vector having all the components equal to zero. Equal vectors are equal if their corresponding components are equal. So all the concepts are same as we have already discussed vectors in plane. And the magnitude of the vector or norm of the vector is also defined by the similar type of expression. We just added z square here. And there are few properties of the vectors. This property is called commutative property. V plus W is equal to W plus V. Similarly, this is associative property. If we have three vectors and you add them in any order, you will get the same resultant. Scalar multiplication, distributive property, and 1 times u is equal to u. So these are the properties of vectors. Well, distance between 2 points in space can be found by the magnitude of the vector joining these 2 points. If we have vector p1, p2, so what is op1 vector here, which is position vector of p1, can be written as x1, x2, x1, y1, z1. And op2 vector, which is the position vector of p2, can be written as x2, y2, z2. So we have already seen in previous slides that p1, p2 vector is op2 vector minus op1 vector. And this can be written as x2 minus x1, difference of two vectors is the difference of corresponding components, y2 minus y1, z2 minus z1. Now, what is the magnitude of this vector is actually the length of this vector p1, p2. So, magnitude of this vector is x2 minus x1 square each of the components, add them, and then take square root. So, y2 minus y1 square plus z2 minus z1 square whole square. So this is the distance between 2 points, which is actually the magnitude of the vector joining these 2 points. So that's all for today. See you next time with the next topic. Take care. Bye.